Welcome to this lecture where we're going to talk about Project Zero runtime trace verification. The purpose of this lecture is to describe Project Zero at a very high level and give you some examples of how it works. We'll talk about the runtime stack of an executing program, what the input, which is called a trace, represents, how to verify or validate the trace, and finish with some common pitfalls. The runtime stack is something that every executing program has. When a program runs, every function call is pushed onto a stack known as the runtime stack. And what is pushed onto the stack is actually something called a stack frame. And that's an area of memory that's reserved on the stack that has enough memory to hold all the local variables for that function. So and we'll talk about this more in a later lecture, but the runtime stack carries enough has enough space to fit all the local variables for each function. So you call a function, and that calls another function, and that calls another function. Each of these get pushed onto the runtime stack in stack frames. When we return from a function, that runtime stack is popped. And so the memory that was being used for that function that was just executing, that just returned, can now be used by some other function that might be called in the future, and it will reuse that same memory, that same area of the stack frame. So just to give you sort of a fake example of this, here's a small program that prints a number from 1 to n recursively. And what it does is, in main, we read in a number n, and then we call print recursively, which calls itself as many times as n exists, right? As many times as the value of n. And so print recursively calls print recursively, calls print recursively, and then as we return from these recursive calls, it prints the value. The details of that are not important. The important part of what I'm trying to show you is that every time we make a function call, the runtime stack, which grows, let's say this way, grows by another stack frame. And so main, the stack frame is here, and it has enough space in this stack frame to fit all of its local variables, argv, argc, which are the two parameters, and n, which is the value that we read in, okay, or that's allocated here. Main calls print recursively, which has exactly one variable, which is the argument to it, and so it has enough space to fit that x. And then it calls itself, which has enough space to fit that x, and that continues recursively. And eventually, we get to call the cout left shift operator to print out at some point, right? And there are some local variables in here. And so that gets called eventually. The runtime stack grows as we make function calls and shrinks as we return from them. So that's the idea. And we'll go into that more in a future lecture again. So for this project, what we're going to do is we're going to validate a sequence of records or descriptions of the function calls and the function returns. We're not going to worry about the local variables that I was just describing. And so the trace, which is the input for Project Zero, is a textual record of function calls and returns during program execution. So every time there was a function called, you would see a line like call read input, where read input is the name of the function. It could be sort of any string that doesn't have any spaces in it. It's just the name of the function. And every time a function returns, you would see in the input return space read input. Okay, that's the way it looks. Now, here is an example trace, and what our goal is to validate that this trace is actually correct, that it has all appropriate calls and returns in a balanced format. So what does it mean for a trace to be valid? We'll go into that more in a minute, but basically every time you call a function, you also return from that function, and you do this so in the proper order. So here's a valid trace, and rather than step through this, I could step through this, but I've written a little demo. Let me show you the demo for this same input, okay? So the demo looks like this. So on the left here, you see these are the inputs. This is the input to the program, okay? And here is where we're going to store a stack. Now, why do we have a stack? We're going to use a stack that we're going to maintain for which functions are currently being called, okay? Those that are currently active. Now, if we look back here, the currently active functions were all those ones that are on the stack. So as we call functions, it grows the stack. And as we return from functions, the stack shrinks. And that's exactly what we're going to see here. The stack will be right here. Right now it's empty because nothing has been called. You can see we're about to call read input. So when we call read input, notice what gets put on our stack. The 0 is just to tell you how deep it is. But what's really on our stack is this read input, the name of the function, okay? The next line is call iStream operator right shift, and so that gets pushed onto the stack. So now our stack has 2 function calls being pushed on. So main called read input and read input called iStream operator right shift. Now the next line is return from iStream operator right shift. So because we're returning, and because we're returning from the function that is currently executing, and you know it's currently executing because it's at the top of the stack, we can then pop the top of the stack. Okay, so it disappears when we read that because we've popped the stack. Then we call operator right shift again, and then we return from it, and then we return from read input. So now the stack is empty. And this is just a fanciful idea. It could be that main is executing outside of here. We don't know. But for the purposes of this trace, we'll assume that the stack can be empty, and we keep going. We call solve, which means we push solve onto the currently running stack, which calls log, and then log returns, and then we call abs, and then abs returns, and then we call the ostream operator left shift, and then we return from that, and then we return from the solve, and now we're done reading the input, and the stack is empty, so it was a successful trace, okay? Now, let's continue on. Traces can be valid or invalid. They are valid if every call has a matching return, and additionally, you check at the, well, that's the sufficient condition, and they are in the right order, okay? Now, the reasons a trace can be invalid are, we might be returning from a function that's not currently called. For example, if the input had these 2 lines, call foo, so foo is the currently executing function, return bar. Well, foo is the currently executing function. It should not be returning from bar, so that's an incorrect behavior, and we would report that as soon as we see it. Okay. Another thing we might see is if the stack was empty and then we saw a return, you can't return from a function when no function is currently executing, so that would be an error condition. And finally, if you get to the end of the trace's input and there's still something left on the stack, there was a foo that was called that never returned, that's also an error condition. So here's an invalid trace, and maybe pause the video, glance at this for a minute, and see if you can identify why this is invalid, but I'll give you a demo in just a sec. Okay, so here's that invalid input. We're going to step through this again. We'll call read input, so we push read input onto the stack. Then we call iStream operator right shift, so we push it onto the stack. Then we return from that. Now look here. We're about to call iStream operator right shift again, so we push it onto the stack, but then we return from read input. Now look, read input is being called, but it's not the innermost called function. It's not the currently executing function. It's a function that called the currently executing function. We can't return from something that's not the currently executing function. So this is an error condition. Okay, so when we do that, we'll identify that there's an error. We're trying to return from a different function. This is not the exact phrase that you should put in your project. Read the project guidelines to figure that out. But this is the point where we would stop processing the trace and report the error and then stop it, okay? So here is the basic algorithm that I just demoed for you. The basic algorithm is this in C++ or in a pseudo C++. We have a stack, and that stack is what we'll call maybe the call stack, and that stores just the names of the functions which have been called, not those which have returned, right? And then we'll step through the input. We'll say while get line cin line. So this grabs a line at a time every time we go through this loop. Then this is, again, pseudocode. You need to split that line variable into both the first portion, which is the first word, which is just the word call or return. And then after that is the function name. whatever the function name is. So you have to split the string line into those two substrings. And you can do that in a number of different ways. If the command is call, then you simply push the name of the function onto the call stack, as you saw in the demo. But if the command is a return, then you have to check for errors like, is the stack empty? If so, that's an error because we can't return when the stack is empty. Or is the top of the stack equal to the name of the function that I'm supposed to be returning from? If not, that's an error function. That's an error condition. But if there is no error, then we can pop the call stack to say that function was being called. It was the currently executing function, but we can pop it now because it's returned. After you get through all of the input, there's still one more check you have to make, and that is to check that the call stack is empty at the end of the program. Okay, so some common pitfalls that you might run into. There's a detail that I didn't go into here, which is that along the way, you need to track the maximum size of the call stack. Not the size of the call stack when the program finished, not the size of the call stack at some point. You just need to track over the lifetime of the program or the trace, how large that call stack got. There's lots of ways of making a mistake when you're splitting the input line into those two words. So try to do so carefully and use existing C++ library code to help with that. Make sure you're reporting only the first observed error. So if there are multiple errors that you can identify in a trace, only report the first one and don't go any further. And of course, you could make a mistake in formatting the output because again, the robot is picky that way. Now, Project Zero should be fairly straightforward for you to do now that you sort of understand how it works. Don't just rely on this video, read the project description very carefully and follow all the directions I gave in a previous lecture about how to approach problem solving for projects in this class. Okay, good luck. Get started on Project Zero. It's going to be fun. Get it under your belt, and we'll move on to bigger and better things.